Now that we know the properties of parallelograms, we're going to learn the converse of all of those wonderful theorems so that we can prove that quadrilaterals are parallelograms. So our first theorem is the converse of the parallelogram opposite sides theorem, which states that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. In other words, if segment KL and segment AC are congruent, and segment LC and segment KA are congruent, then we can see that the quadrilateral KLCA is a parallelogram. Notice the parallel markings here and here. As always, I want to walk through the proof with you. So in order to help us out with this, let's draw in segment AL here. That is congruent to itself by the reflexive property of equality. The two triangles are going to be congruent by side, side, side. Now, if the triangles are congruent by side, 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 then we know that their corresponding parts are also congruent. These two angles happen to be alternate interior angles. And since they are congruent, the lines are parallel. Likewise, segment LC and segment KA are parallel. And wow, if opposite sides of a figure are congruent, then the figure is a parallelogram. Can you see how that's going to work? The next converse that we're talking about is the converse of the parallelogram consecutive angles theorem. This one states that if an angle of a quadrilateral is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. So in our figure, that means that if angle A and angle K are supplementary, and angle A and angle C are supplementary, then quadrilateral KLCA is a parallelogram. So let's take a look at this one. If angle A and angle K here are supplementary, well, we have two lines cut by a transversal in such a way that same side interior angles are supplementary. That tells us that the two lines are parallel by the converse of the same side interior angles theorem. Likewise, it tells us that the lines are parallel. That's basically how you would go about proving that one. And our next converse is the converse of the parallelogram opposite angles theorem. This says that if both pairs of opposite angles in a quadrilateral are congruent, then the quadrilateral is a parallelogram. So notice in our figure that angles A and L are marked as being congruent, and also angles K and C are marked as being congruent. That means, once again, that quadrilateral KLCA is a parallelogram. How can we go about proving that one, you ask? It's not as hard as it would appear. What we're going to do is we're going to assign some variables. Let's say that the measure of angle A is, I don't know, x is always a good variable. If that's the case, then the measure of angle L is also x. And let's say that the measure of angle K is B, which, because they are congruent, that also means that the measure of angle C is B. And remember, if we add all four angles of a quadrilateral together, the polygon angle sum theorem tells us that a quadrilateral's angles will total to 360 degrees. So let's do some simplification here. 2x plus 2b is going to equal 360 degrees. That's the distributive property of equality. Oh, but wait a minute. I see that we have a 2 here and a 2 here. That means that a 2 has been distributed to both terms. So if we use the distributive property of equality in reverse, that gives us 2 times the quantity x plus b, and that, of course, is still going to equal 360 degrees. Now, we don't want that 2, of course, so let's divide that 2 into both sides of the equation, which tells us that x plus b is equal to 180 degrees. Well, wait a minute. X also happens to be the measure of angle A. Likewise, B is the measure of angle K here. That tells us that angle A and angle K are supplementary angles. That's the definition of supplementary angles, isn't it? But wait a minute, that's not all. B also happens to be the measure of angle C here. What does that tell us about angle A and angle C? It tells us that angle A and angle C are supplementary. And I think we just proved a theorem about that. If an angle is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. So I will leave you to fill in the blanks to all the proofs. Let's use these theorems to help us solve some problems here. For what value of x and y must MNOP be a parallelogram? Now look at the variables. They're going to give you a clue as to how to set up the problem. For example, if you notice the lengths of PM and ON, they have an x and a y in them. If we were to try and set up this equation, it would not be happy because we don't know how to solve an equation with both x and a y. However, notice the lengths of PO and MN. They both have x's in them. We can solve an equation with just x's. And because we want this to be a parallelogram, we can use the converse of the parallelogram opposite sides theorem, which says that if the opposite sides of a quadrilateral are congruent, or rather their lengths are equal, then the quadrilateral is a parallelogram. So now we can just do some simple algebra here. The subtraction property of equality allows us to subtract 3x from both sides of the equation. The addition property of equality allows us to add 18 to both sides of the equation. And the division property of equality allows us to divide both sides by 5. So that tells us that x has to be 5. We now know that x has to equal 5. But what about y? Well, this is the nice thing about doing x first. We can now use the other sides of the parallelogram and use the same converse to force the sides to be congruent. But what we'll do is we'll substitute in the 5 that we found for x into the expression on the left-hand side here. So 5 times 5 plus 2 is going to equal 3y. 25 plus 2 is 27. And then we'll use the division property of equality to find out that y has to equal 9. So that's how we can use algebra to determine values of variables to force quadrilaterals to be parallelograms.